long ago that we did it? 2 weeks ago. Does anybody still remember? Does anybody still need the handout from 2 weeks ago? No. No chance. Just forget it. Is that what you're saying? Okay, so we were trying to solve this problem. As a reminder, there was a certain number of projects. Each of the projects can start in a certain month. For each of the projects, there's a certain profile. So you have got to bring the actual data book. I don't know where I've put the data. Seem to be forgetting things. Anyway, so got a project that uses some resource. There's only one resource because it's a simplified situation. But you can imagine it's using some vehicles that you need for building or things like that, or people with different skill sets and things like that. So let's say can get quite complicated very quickly. So here in this example, there's only one resource, and for every project, you have a kind of a resource profile that you use. So for example, in the first month that you're working on it, it needs 3 units. In the next month, it needs 4 units. And in the third month, it needs 2 units. And after 3 months, it's completed. And from the time when it's completed, you start earning some benefits. Okay, so the project gives you BP, project B gives you BP every month after it's finished. And we're looking at a period of 12 months or something like that. Well, I don't know how many, but that's the idea. Now, the question is, when should you start each of the projects that you have? You have a finite list of projects, and what month did you start every project in? So you maximize the total benefit that you get in the end. And yeah, that's the question. So what you must not exceed is the availability of the resource in any single month. Okay, does that make sense? Okay, so that's the That's the question. What is the answer? Well, the answer is we want to solve it using integer programming because it's quite nice. Yeah, this is a bad day today. Okay, so what we had was so using to summarize the data that we had, set of projects, set of months, capital N months. You pick your N. Duration of every project, which is how long it takes, how many months it takes. And then the resource. So for every project, in every month of executing it, you need the resource, and then that's the benefit, and how many months you need the benefit, and then this is how much of the resource is available in a particular month. Okay? So those are the data that you get, and the formulation started by saying what the decision variables are going to be, and that's where we ended. Okay, well, because we said that the decision variables, and this is important, so look at it again. You'll have 0, 1 variables, and there will be, like for every project, you will have in each month 0, 1, whether you're starting in that particular month. Okay. So these are the decisions. The decision is for every project, when should I start it? And yeah. That's the zero ones. And there are no more decision variables. So that's quite simple in terms of decision variables, and that makes the constraints a bit more difficult. Or did you want the objective first? No. Constraints. The objective is a nightmare, like 3 lines in my thing. Okay, so one of the constraints, well, one of the kind of set of constraints or type of constraints that you have with decision variables like this is that you don't really want too many of them to be 1, because you only want every project. You don't want to start the project several times. You can only start it once, not once. So this will be one set of constraints which says that you can only start each project once. Now, it depends on what the precise situation is. Sometimes you have, these are the projects, and we have to do them all. Sometimes you have, these are the projects, and we're picking which ones to do to make maximum benefit. And depending on that, you'll have the constraint. So if we're assuming that the list of projects is the projects that you have to do, all of them, then you'd say that so the sum of all the starting times of project M. So this is not the starting times really, but so this has to be exactly 1, because you need to start every project exactly once. Okay, and the sum is you go through all the months. So the months go from 1 to capital N, and you have a constraint like this for every project. Okay? Doesn't make any sense. You've got all these zeros and ones for all the projects, and you want them to sum to 1, which means that exactly one of them will be 1, and the others will have to be 0. And that's what you want. And if you were picking which projects to do, then you just put less than or equal to 1. It would mean that you don't have to start it sometimes. And then there was some narrative about limited resources. I started the constraint about limited resources, and it seems obvious that this is how it should be. Within every month, in month N, that's how much resource you have available. So now it's just a matter of creating a formula which, based on these SPMs, gives you how much we need in every month. And that's a complicated formula. Okay, so that really is a complicated formula. I'll put it down. So it's a sum from 1 to little m r project P m minus t plus 1 times s p t. This is not finished yet, but I want to explain it. Or you look at it and you explain it. Try to pass it. Not at all. It is not finished yet. Okay, so when you look at so what does this mean? We're trying to make sure that in month M, at this end, we're not using more than this much resource. Is that clear? That bit is clear. Now, why does this? This doesn't give us how much resource we need altogether. This gives us how much resource we need for project P. And the amount of resource we need for project P depends on when we started. Okay? We started later than in month M. I think this is month 4 we're looking at. So if we started in month 5, 6, 7 or so, we don't need any resource for it because it hasn't started yet. Okay? Now if we started before month 4, or in month 4, then the amount we need is the amount of resource for project P. Now, if we started it in month 4, so SP4 is 1. Then this is 4 minus 4 plus 1. So this gives us how much resource it needs in the first life of it, first month of its life, the project. Okay. If we started in month 3, so then T is 3, M is 4. 4 minus 3 is 1 plus 1 is 2. So this is telling us how much resource it needs in month 2. And if we started it in month 2, then in month 4, it needs 4 minus 2 is 2 plus 1 is 3. So this is telling us how much it needs in the 3rd month of its life. So it works. Do you believe it? Well, if not, you'll have to process it again because it's gone. This is a good time. So Taiba agrees that this is how much project P needs in month M. And if you have any questions, go to them. And what we need to do is just add them all up for all the projects. Okay? And then we have to say that this is a constraint for each M. What? shaking your head. That means something's wrong. Okay. It's gone. And we have to say one last constraint. What is the last constraint? What was always the last constraint in linear programming? Non-negativity. So in integer programming, we need to list all the requirements we have on the variables, whether we want them non-negative and can be real, or non-negative and integer, or binary, so 0, 1. Okay, so in this case, we want them all to be 0, 1. So for all the projects and all the months, we want this SEM to be 0 or 1. That's all the constraints. Now, the objective. So if you look at a project and it starts in a certain month, what is its benefit going to be? Yeah. Okay, so in every month that it's finished, it's going to be BP. Okay. Now we have to multiply this by the number of months that it's finished for, and the number of months that it's finished for is this. Apparently. So this capital M is the total number of months that we're counting for. And if it starts in the first month, so this would be 1. So this is, and it takes this many months to finish, and this is the time before it's finished, that after it's finished, that until the end of our planning period. And if it starts later, then we have to subtract how much later it starts, and that gives you how many months it's finished. Okay. That's this. So the objective, and obviously, is to maximize the benefit. Maximize. We have to add them over all the projects. And we have to add them over all the months. these are all the possible months when the project can start. Can't start after it's already too late for it to be finished. And this is the benefit that we had. And each of the benefits we're either counting or not, depending on whether we start the project in that month or not. So if it starts in month N, then we're doing it for N. That's the objective. Okay, it's a lot of formulas, so it's quite hard to sight read and process very quickly, but that's the formulation, so you need to sit down and have another look at it. It's quite an interesting problem. It was actually a challenge in operational research. I can't remember who ran it. I think it was one of the French energy companies, something like that. And teams of operational researchers were running it, and there it was more complicated because there were not only there were resources, but there were technicians, and the technicians had to be assembled into teams, and every day you could have different teams, and then each of the technicians had some skills, and for certain jobs you needed a certain skill set, and so on and so on. So that was a more complicated version of this, essentially. And they couldn't quite solve it, really, because it got too complicated and too long. And there was a student here, Amy, who actually did a whole PhD at NMU, solving a problem like that. So it can get quite complicated very quickly. But she got a good job. I think she's working for IBM in London now. She graduated last year. So it's nice and useful and all that. Any questions or objections? I can see that. Okay, the next thing I wanted to do is SOS constraints, but I won't do SOS constraints because I've been talking too much about this already. So you can read about them in the homework problem. So gets one. And I'll do something completely different. Who's already started the first assignment, solving IOPs? Well, the first, JF3, JF4. Started? Have you finished everything? Why not? Because there is a question that asks you to produce a valid inequality or a cutting plane. And we haven't done it yet, have we? So now let's do it. I think we'll probably only get to the actual assignment question method next week. At least that's what the plan says. The idea is to add new constraints. And I don't know what I meant to do here. Oh, now I can see what I meant to do. So, look at this. This is an example problem. Do you remember it? If you don't remember it, doesn't matter, because it doesn't matter. What's the point? The point is, if I if I draw the straight line here, it's not very straight, but it's straight because I tell you it is. And it goes through this point here. It doesn't look like it does, but it does. And if I look at everything that's on the left, these are all the points that satisfy x1 minus x2 is less than or equal to 1. Is that right? Okay. It's a line, so it suffices to check it for 2 different points. So, okay, so this one is coordinates 1 and 0. 1 minus 0 is less than or equal to 1. Yes. This is 2, 1. 2 minus 1 is 1. Yes. So it is indeed the line with equation x1 minus x2 equals 0. And 0, 0 satisfies this, so it's this half. Yeah, I'm right. This is a huge difference between philosophy and mathematics. Philosophers believe they're right and have no way to prove it. Mathematicians always doubt themselves, but they can prove that. Okay, so now you can see that there are some yellow points that don't satisfy this equation. Sorry, not equation, but inequality. Okay? So if I looked at the linear programming problem without the integer word there, then I couldn't just add this constraint without changing the feasible solutions. Because these ones would become infeasible. They were feasible before. But if I'm looking at the integer solutions, the feasible solutions are just these dots over here. And it doesn't look like that, but I've included them all. So they're all the feasible solutions, so the dots within the yellow region and the boundary, they're still feasible if I add this constraint. Okay? So this is called a valid constraint. It's a valid constraint because it's satisfied by all the integer feasible solutions. So that's an example. I'm drawing another example. So this is x1 plus x2 is less than or equal to 3. It's not.
Top of the yellow region is x2 is 4, or x2 is 3, and x1 is 2, which makes it 5, which is less, it's not less than 3. It's the line x1.
That's true here.
X1 is always less than 3.
You see, this is another difference between philosophy and mathematics. In philosophy, if the authority says something, the students are not allowed to doubt it. But in mathematics, if the teacher says something that is completely wrong, the students are expected to actually doubt it. Okay, so x1 is less than or equal to 2. Is that what you said? Okay, thank you. So that's another one I love. Do you agree? Follows from the picture. But we need to devise a way to actually find them without pictures. And that's what the rest of today and next week is basically about. So if you had these two inequalities, valid inequalities, how would you solve the integer programming problem? Yes, and it is. How would you solve it, Alan?
So,
Relax it. What would you find?
integer solutions.
Why?
Because all the points of intersection.
Because, I'll put it into a fancy word. So the basic feasible solutions are the corner points. And the corner points all have integer coordinates. So if you solve it using the simplex method, no matter what the objective is actually, you would find an optimal solution which is in one of the corners. And so you would find an integer solution just by solving the linear problem. That's a neat idea behind these cutting planes algorithms. It is to try adding valid inequalities and resolving the relaxations, and then at some point you find them all, more or less. Okay. Yeah. So that's the idea. What's the implementation? I have an example. It's a silly example. So for binary constraints, you can sometimes get very silly examples. So, for example, what happens if x2 and x4 are 0? Okay, who doesn't know what the binary variable is? Binary means that it can take the values of 0 or 1 only, like we had in the project plan. So what happens if x2 and x4 are 0? Well, then we get 3x1 minus 0 plus 2x3 minus 0 plus x5 is less than or equal to minus 2. Is that possible? Why not?
Regardless of like if they're all zeros, then it should be 0.
Yeah.
If all of them were 1s, then it would all be positive. And then if coefficients of x, you would be able to get less than 1.
And if there were some zeros and some ones, then still it's always positive. So it can't be less than minus 2. So that's not possible. So if that's not possible, that means that this is not possible. That x2 and x4 are both 0. So at least one of x2 and x4 have to be 1. So x2 plus x4 has to be at least 1. And so this is a valid inequality. This is an example of the way how you find valid inequalities. I think it's not very clear how you come up with things. You know, you don't need a picture for that. It's a warm-up. Basically a warm-up. Another warm-up exercise. Is it possible that x is x2 is 0? Is that possible? Why not?
X against the x4, only if x4 is 1, that still takes you to 0 plus whatever x3 and whatever x5. And because those are both positive, you would be able to get less than that.
Yes. So I repeat that. Everybody heard it all right? No? Say it again. Okay, I'll read it. Okay, so how could you make this less than or equal to -2? Well, the best thing you can do is set x3 to 0, and x5 to 0, and x4 to 1. Because if you set x4 to 0, then. But even if you do that, you're only getting 3 plus 0 minus 3 plus 0, which is 0. You're not getting something that's below -2. So there's no way of putting 3x4 and x5 to 0 in once and get anything. Okay? So that's not possible. So what is the valid inequality that it gives us? Great question.
If we set x2 to 1, x1 to 0, make the order get -4.
You set x2 to 1 and x1 to 0.
Yeah, and then set the orders to 0 as well. You get -4.
Good. So it doesn't prove anything. But yeah, that's good. Okay. I'm still stuck with this one though. Because there's a missing bit. good observation. But what you want is to prove that something is not possible, not that something is possible. And when you prove that something is not possible, you can add a valid inequality. Like here, we prove that it's not possible that they're both 0, which means that when you add them, they have to give you at least 1. Yeah, because so this gives you a valid inequality. This is not possible, which means that x1 can't be larger than x2. This in binary ILPs, this is expressed as x1 is less than or equal to x2, I think. You need to check that I'm writing it the right way. So you can't. So what you can't do is put this one to 1 and this one to 0. And this is exactly what this inequality prevents you from doing. And any other 0, 1s satisfy this. Okay? It's an important, even for formulation problems, when you have questions like if something, then something, usually leads to something like this. Okay, that was the warm-up. Go on to another warm-up. No? I want another warm-up. One last warm-up. Okay, so what happens if you divide this constraint by 11? Why 11? Because I tell you so. So what do you get? 13 over 11 x1 plus 20 over 11 x2 plus x3 plus 6 over 11 x4 is less than or equal to, well, I don't know what that is. Something about what 6 in the bit. So this is a valid inequality. Yes, because it's the same inequality as the one we started with. So whenever your integer program contains this is also valid because it's the same. Now, watch this trick. X1 plus X2 plus X3 is less than or equal to 72 over 11 is valid. Have you seen the trick? You don't believe it. Yes. Well, no.
Even if the one to be less than 2 it's actually 6.
Oh, they don't have to be just 0, 1. They have to be longer. Same thing. In fact, what happens is the following. So here you have a coefficient of 1, and here you have something that's more than 1. So x1 is less than or equal to 13, 11 x1, because x1 is non-negative. So if you have something that's positive, and you only take it once, then you get less than if you multiply by 13, 11. Yeah. And if you have, this is more than 1, so if you take x2, which is positive, you get less than 20 over 11 times x2. And x3 is the same. And if you take 0, that's no more than 11 times 4. Okay? So each of these is less than that, that's less than that, and well, that's the same, and the 0 is less than that because they're all non-negative. So this is valid because these variables are all greater than or equal to 0. Not even using the fact that they're integer, but I'm replacing every coefficient with something smaller, so I get something smaller. Does that make sense? This is very important, so everybody please understand. Not a very good teaching method. I'll give you a 5 if you understand. Okay. I'll demonstrate. If x1 is 11, what am I getting here? What am I getting here? Okay. If x2 is 22, what am I getting here? What am I getting here? 40. 40 is more than 22. If x3 is 15, what am I getting here? Yeah. Okay, that's the same. If x4 is 70, what am I getting here? And there's something. So each of them is smaller than that. Okay, so therefore, this whole thing is no more than that, and that is no more than that. So this whole thing is more than that. Last trick is coming. X1 plus x2 plus x3 is less than or equal to 6 is valid. You agree? Who agrees? Okay, good. So I don't have to explain. Because these are all whole numbers, so when you add 3 whole numbers, you get something that's less than 7. Well, it can't be more than 6. And next week, we'll use these ideas to the whole thing. Good night and good night.